Okay, so we have seen that finite dimensional linear vector spaces, have representations. All operators which live on finite dimensional linear vector spaces have matrix representations. So if we understand matrices well, then we understand finite dimensional vector spaces. And so therefore we are going to look at a number of properties of matrices starting from this lecture, which is about eigenvalues and eigenvectors, right? Certain properties of eigenvalues and eigenvectors will be discussed here of matrices, and then more properties in the context of eigenvalues and eigenvectors will come up later. But let's look at a few very important results in this lecture. Okay, so we start with this crucial result that every n by n matrix has at least one eigenvector, right? So how do we find eigenvalues and eigenvectors? We start with the eigenvalue equation, right? So you have A times x is equal to lambda x. So we need to find vectors x, and we need to also find the scalar lambda, right, which is in general a complex number, right? So we need to find a way to compute lambdas, and corresponding to lambdas, x is corresponding to those lambdas. So what we are really interested in is finding a solution to this equation, right? A minus lambda I acting on x equal to 0, right? There's a matrix which operates on a vector, on a column vector, and it gives you a 0, right? So this is, if you recall from many lectures ago when we were describing linear equations, right? So this is really a set of homogeneous equations, and therefore it can never be inconsistent because all the stuff on the right hand side is 0. Now the only question is, does it have only the trivial solution or does it have non-trivial solutions, right? So we have seen that the condition for the non-trivial solution to exist, right, when you have n equations and n unknowns, right? So we are looking at a square matrix, so the number of rows in this equation is the same as the number of unknowns, right? So we have exactly the situation tailor made where we had a determinant condition for this, right? For this to have a non-trivial solution, the trivial solution is of course the case where you take all this vector x to be 0, and in which case you don't call it an eigenvector, it's a null vector, right? So an eigenvector, for it to be an eigenvector, you must have a non-null vector. That's what we're looking at, that's what we're interested in, right? So the point is that this n by n matrix has at least one such genuine eigenvector. So it is a square system, and that means it has n equations and n unknowns. So this means that for this to have a non-trivial solution, we must demand the determinant of a minus lambda I equal to 0, right? And this is what is called the characteristic equation corresponding to this matrix. And now this is a polynomial. Determinant of a minus lambda I is a polynomial of degree n, right? So this comes from the property of determinants. You can try to expand determinant of an n by n matrix, and then you will see that if there is a coefficient like this, for sure it's going to be a polynomial of degree n with complex coefficients, right, in general. And so there is this fundamental theorem of algebra which guarantees that a polynomial of degree n with complex coefficients has at least one root, right? And let's call this lambda 1. So in fact, actually the fundamental theorem of algebra implies that there is going to be exactly n roots for an nth order polynomial, nth degree polynomial, and although some of these roots may be repeated, right? So you will be able to factor this polynomial as lambda minus lambda 1 into lambda minus lambda 2, so you can in general write it as lambda minus lambda 1 to the power k1 times lambda minus lambda 2 to the power k2, and so on. All these parameters k1, k2 and so on must add up to n. So that's a consequence of the fundamental theorem of algebra. So there is at least one root, so let's just call that lambda 1, right? So there would be only one root if all the roots are repeated. If you have a scenario like lambda minus lambda 1 the whole power n, then there is only one root. But in general, you could have more roots. Okay, so it has at least one eigenvalue, and that is lambda 1, right? In fact, it has n eigenvalues, right, some of which could be repeated, right? So let's call this root that we have as lambda 1. Now given one eigenvalue lambda 1, we can go back and plug this in here, right? So and we have to find a solution to this homogeneous equation, which is definitely possible. So you can find an x1 such that a minus lambda 1 I times x1 is equal to 0, and you will find a non-trivial solution, right? Therefore you will find a non-trivial vector corresponding to a certain eigenvalue, right, lambda 1, and therefore you have at least one eigenvector. Every matrix has at least one eigenvector. So in fact, you can make a stronger statement here. In fact, every non-repeated eigenvalue will yield a distinct eigenvector, right? So the same argument will hold. So in place of lambda 1, suppose you have a lambda 2, which you have managed to find. These are all roots of this polynomial equation. So if there is another root, then you can go back and plug this into your homogeneous system of equations, and our understanding from systems of linear equations guarantees us, because the secular equation or the characteristic equation holds, guaranteed that you will be able to find a non-trivial solution for x. So you will get a distinct eigenvector corresponding to a different lambda 2 and a different lambda 3 and so on, right? So there are as many distinct eigenvectors as there are distinct eigenvalues for any matrix. So in fact, we can make a stronger statement, which is the next result, which is that every distinct, that the set of distinct eigenvectors which are derived from distinct eigenvalues are all necessarily linearly independent. Not only are they distinct eigenvectors, but they're also linearly independent. Okay, so eigenvectors of a matrix corresponding to distinct eigenvalues are necessarily linearly independent. To show this, let's start with just two distinct eigenvalues, lambda 1 and lambda 2, and then we will proceed by induction, right? So we have lambda 1 and lambda 2 and two eigenvectors x1 and x2. So you have A acting on x1 is equal to lambda 1 x1, A acting on x2 is equal to lambda 2 x2. So we want to show that if lambda 1 is not equal to lambda 2, then x1 and x2 are linearly independent, right? Which means that suppose x1 and x2 are not linearly independent, right? So that would imply that x1 is equal to alpha times x2 for some coefficient alpha. If this holds, let's see that there is a contradiction. If a x1, then let's operate with a on x1. So you have a x1 is equal to a times alpha x2, because x1 is equal to alpha x2. That will give us alpha times a x2, which is the same as, a x2 is lambda 2 x2. So you have alpha lambda 2 x2. Now if I exchange these coefficients, the order, and then I have lambda 2 times alpha x2, but alpha x2 is the same as x1. So I have managed to show that ax1 is equal to lambda 2 x1, right? But we know that ax1 is lambda 1 x1, right? So what we have managed to show is x1 is an eigenvector of A, but with eigenvalue lambda 2. Now, but we have, the it's part of the proposition that lambda 1 and lambda 2 are distinct eigenvalues, right? So which is impossible, and there is a contradiction with what we have just shown, which is that the eigenvector x1 has eigenvalue lambda 2, right? So there is no way that this statement and ax1 is equal to lambda 2 times x1 can be consistent with lambda 1 not equal to lambda 2. So the only way this can be avoided is if our initial assumption is wrong. So x1 and x2 are not linearly dependent. So x1 and x2 are linearly independent, right? So we have managed to show it for just two distinct eigenvalues, and then by induction we can show that this holds also for an arbitrary number of distinct eigenvalues, right? So let's suppose that you have distinct eigenvalues lambda 1, lambda 2 all the way up to lambda q, and let's say x1, x2 all the way up to xq are linearly independent eigenvectors, right? So now we'll show that if we put in one more eigenvector xq plus 1, and corresponding to a distinct eigenvalue lambda q plus 1, necessarily this new set x1 all the way up to xq plus 1 also must be linearly independent, right? To see this, suppose we make the assumption that the moment you add xq plus 1, the set is not linearly independent. So that means the set is linearly dependent. So we'll be able to find some non-trivial coefficients alpha 1, alpha 2 all the way up to alpha q plus 1 such that this relation holds, summation over alpha k times xk is equal to 0. Now immediately we observe that the q plus 1 coefficient alpha q plus 1 cannot be 0, right? If it is 0, then it would imply that these vectors x1 x2 all the way up to xq are linearly dependent. So this would be a contradiction. So we must have that this coefficient is non-zero, and so we'll be able to express xq plus 1 in terms of the other eigenvectors. So we'll be able to divide throughout by this coefficient, and then we have xq plus 1 is equal to minus 1 summation over these constants times xk, when now k runs from 1 to q, with at least one of these coefficients which is non-zero, right? So now if we operate with a from the left side, so we have a acting on xq plus 1 is equal to minus summation over all these coefficients times a acting on xk, but a acting on xq plus 1 is the same as lambda q plus 1 q plus 1, right? So and then again here in place of a xk we can replace it with lambda k xk, and then in place of xq plus 1 we will again plug back this equation, right? We have already written xq plus 1 in terms of all the xk's. So in place of xq plus 1 we'll plug in this expression, and then we have this expression follows from plugging in place of xq plus 1 this equation, and then if we rearrange all these terms we are able to write this as a summation over k of bunch of coefficients. You have alpha k by q plus 1 times this difference of these eigenvalues times xk is equal to 0. Now, so what do we have here? We have the sum of some coefficients times this vectors xk is equal to 0, but xk, k going from 1 to q are linearly independent. So that means that the only way that this can happen is if all of these coefficients are 0, right? And from here we know that at least one of these coefficients alpha k is non-zero, because if all of these were 0, then there would be a contradiction to this earlier proposition. So therefore at least one alpha k is non-zero, and that would immediately imply that you'll be able to find some lambda q plus 1 must be equal to one of these lambda k's for k going from 1 to q, right? So it's not a very difficult argument. You just need to go over it carefully, and then you can convince yourself that if we make the assumption that x1 x2 all the way up to xq are linearly independent, that implies that x1 x2 all the way up to xq plus 1 also must be linearly independent, because this is going to lead you to a contradiction. It's not sustainable with the condition that all these eigenvalues have to be distinct. So we have managed to show that there's a contradiction with that assertion, right? So the only way that this could have been avoided is if we had not made this initial assumption, which is that this box of vectors x1 x2 all the way up to xq plus 1 is linearly dependent. So they have to be linearly independent, and so that's all. That's the result. So what we have managed to show is if you have a matrix with a bunch of distinct eigenvalues, then each of these distinct eigenvalues gives you a distinct eigenvector, but not only a distinct eigenvector, but the set of eigenvectors obtained from these distinct eigenvalues is in fact going to be a linearly independent set. And this has consequences when all the n eigenvalues of your n by n matrix are distinct, right? So what we can immediately tell is that if you have an n by n matrix with n distinct eigenvalues, then you have n linearly independent eigenvectors. And so we have seen this result, many lectures ago, that if you have n linearly independent vectors in an n-dimensional space, then they form a basis, right? So here we can take all these n linearly independent eigenvectors and form a basis, which means that any vector in the space can be expanded in terms of these n linearly independent eigenvectors. So this is a scenario which is called, it's a completeness condition, right? So matrices whose eigenvectors span the whole space are complete, right? So this is of crucial importance in quantum mechanics. Any physically meaningful observable, there is an operator corresponding to an observable, and every such operator corresponding to a physical observable must yield eigenvectors which span the whole space. If it does not, then there is going to be an inconsistency in quantum mechanics, and that's why we work with Hermitian operators, right? So real quantities correspond to operators which are Hermitian, as you might have seen in quantum mechanics. And so we have already seen that Hermitian operators have this property of completeness comes about because of linear independence of various eigenvectors. So we will return to this in the context of matrices a little while later. But the main point, the main take-home message from this lecture is that if you have an n by n matrix, for sure it has n eigenvalues. Although there are some of these eigenvalues may be repeated, but to be sure that you have n linearly independent eigenvectors, right? So that's not always the case, right? We will look at more examples of this later on. But in this lecture, we have shown that if you have many distinct eigenvalues, each of these distinct eigenvalues will give you a distinct eigenvector, which also form a linearly independent set. And the particular case of interest here is if you have an n by n matrix with n distinct eigenvalues, then for sure your matrix will yield n linearly independent eigenvectors which can form a basis for your space. That's all for this lecture. Thank you.